Hello students, today we are in lecture number 52. Lecture number 52 of 4th chapter, moving charge and magnetism. My dear student, today we will continue the topic that we have studied in last lecture. It was magnetic field at axis of circular coil. We left with one topic. It was magnetic dipole moment that we will cover today. I am B.S. Pandey. My dear student, for a circular coil having n turns, we have found that the magnetic field at axial point, it was obtained at point P as BP, or yes, PP if it is the center O. This is the position X and the radius was R. We have calculated the magnetic field in vector form as mu naught I pi R square divided by 2 pi R square X square thrice of 2 I cap, and for n turns we have seen B is mu naught Ni pi R square can be written as A divided by 2 pi R square X square 3 by 2 I cap. We have studied till here. Now, today we are having the topic, it is magnetic dipole moment. Magnetic dipole moment. My dear student, as we have discussed electric dipole moment, in which we study there should be two charges of equal and opposite nature. In same way here, in magnetic dipole moment, my dear student, the combination or the system in which there will be two pole of magnet exist. Okay, remember, my dear friends, every current carrying loop act as a short bar magnet, and that's why it is considered as a short dipole. Okay, look at here. What we have actually studied, on the basis of that one we are going to make here diagram. Suppose we are having the n number of turns of our conductor, like this way. This is the n number of conductor. Now, if you will see the axis of this conductor, this one is very important, my dear students. If you see the axis of this conductor, if current is flowing in this direction, let me draw the direction of current using this reading. Okay, in this direction, if current is flowing, then you will see if in this direction current is flowing in this direction, if this is the coil, okay, and current is flowing in this direction, then there must be, using this right hand, as I told you, to find the direction of magnetic field, you use your right hand thumb rule. Okay, so you will find current in pattern of current. This forefinger, the thumb is goes in this direction. So this will be the direction of magnetic field. let me draw here the direction of magnetic field. This is the direction of magnetic field, that is from little away from the loop, the magnetic field goes in this way, and after getting it makes a loop this way, my dear student. Now, if magnetic field lines direction in this way, this is the magnetic field lines, remember, magnetic field lines, it means you can see magnetic field lines enter from this section and exit from this face. It enters from this face and exit from this face, and this is making the closed loop, which can made by only the magnetic field lines, the closed loop. Electric field lines never makes closed loop. So, my dear student, you can compare this one with a short bar magnet. You can see if this is the bar magnet, this is the bar magnet having north pole and south pole. Actually, from north pole, magnetic field lines exit in this way. So magnetic field lines goes in this way. Inside the magnet field lines continues to make the closed loop. Now you can compare both the diagram. You will see there is a similarity. It means a current carrying loop considered as a bar magnet. Okay, and the phase at which the field enters, this is the south, and the phase from which the field lines exit, it is north. It means all the current carrying conductor behaves like a short dipole, like this magnetic dipole act. Okay, if this act as a short dipole, it means this a bar magnet, it means this is a dipole also. Now if this is dipole, so we can study about the dipole moment, my dear student. Okay, so give the heading dipole moment. Now the one thing which is also very important to find which phase is south pole and which phase is north pole, because this particular topic you will use in electromagnetic induction when we will study about the Lenz's law. Okay, so let me clear over here that which phase of the coil you will treat as south and which one as north. Remember, my dear students, if you are having a coil, listen carefully, if you are having a coil and the current is flowing in this direction, all right, and you are looking the coil from this phase and the current is clockwise, so if you will see the coil from the back face, you will see it is anti-clockwise, and this is very, very amazing. Okay, this is the coil, you are looking, the current is in this direction. As you will look at here, as you will invert the coil, you will see now the direct flow of current is inward. It means one phase, if it is clockwise, then another phase you will find it is anti-clockwise. Okay, and this is a very important to study while the finding north pole and south pole. Now if current is moving in this direction, you can see current is in this direction. Okay, so the magnetic field lines goes in, and the magnetic field goes in the phase, it is called the south pole. So let me write here the S for the south pole. Now after writing the S, you can make the arrow at end of this letter, and you will find that this arrow obey the direction of current, which is perfect, which is similar. If this arrow follow the same pattern as this arrow, it means you have written this letter correctly. and if you will write correctly this letter, then you will find this is perfectly the pole same. All right, so if current is moving in this direction, this will be considered the south pole. You cannot write north over here. Now the opposite face, the phase 1 and phase 2, this is the second phase of the same coil. Okay, so in same coil you will find the current is moving in downward direction, and if it is downward direction, then you need to write here the N, north pole. After making this arrow, you will find, yes, it obeying the direction of current. So this is the north pole and this is the south pole. This is the short trick to find the north pole and south pole. Whenever you find the direction of current, try to write down north and south. Remember, if you try to write north over here, you will find no, it is incorrect. Look at here. If I'm writing north over here, okay, you can see the direction of current is not obeying. So this is the proper way to find the north pole and south pole, my dear student. Now you should give the heading magnetic dipole moment. I'm going to define this magnetic dipole moment, and I'm also going to give a simple formula. Okay, let me grab this and this too. So my dear students, write down magnetic dipole moment. It is defined as the product of current and phase area of the coil. Okay, magnetic dipole moment mu, it is defined as the product of current and phase area of the coil, that is pi r square, or mu is I times A. All right, for n turns, this will be for n turns, this could be written as mu is equals to NIA, and this is the magnetic dipole moment. Now that equation that we have obtained, you can write in this magnetic dipole moment, okay, in this form of magnetic dipole moment. Now for circular coil, we can write the magnetic field as mu naught, it was NIA for n10 actually, I'm telling my dear student, divided by 2 pi r square plus x square 3 by 2 I cap. Yes, it was. Now this NIA can be written as mu. Alright, and this is a vector quantity, remember. Mu naught times mu divided by 2 pi r square plus x square 3 by 2 I cap. In magnetic dipole moment, you can write this equation as this one also. This mu is vector quantity, remember, vector, okay, and the direction obtained by the direction of current. If this is a coil, current is moving this direction, so if current is moving in this direction, magnetic dipole moment will be in this direction basically. Okay, in the direction of magnetic field, you can give the magnetic dipole moment, the direction of magnetic dipole moment. All right, I hope that you got the magnetic dipole moment. It is NIA for n turns, and simply it is the product of current flowing through the conductor and the phase area of the conductor. Okay, one very simple question, my dear student, I'm telling you a very simple question here. Suppose if you're having a coil like this one, and this coil is connected with a battery source. All right, this is the plus terminal, minus terminal, so the current is moving this way. Current is going from this to this. This is your axis. Okay, now we place a magnet over here and north pole and south pole. Now this magnet actually either attract or repel. Which one is the correct answer? Whether this is fixed, coil is fixed through which current is flowing. Okay. Now this magnet will repel or attract towards the coil. You have to find the answer. Try to find out the answer. Okay, now let me give you the answer. If the current is moving in this direction current is moving, so this magnetic field will be produced in this direction. This is the direction of magnetic field, and this becomes south pole, and behind this will be the north pole. It means the south pole near the north pole, so this magnet will be attracted. So the answer is it will attracted by the coil. All right. Now the next question, my dear student, I will discuss. Suppose we are having two coaxial coil. Okay. This question has been asked in board, I think. I don't remember the year exactly, but this has been asked in board examination. The two coaxial coil all right, this way, with the separation of 2r, it is kept. This is r and this is also r, the radius, both the identical. Now the flow of current is also same with the same magnitude I. At the center O, all right, at the center O you have to find the net magnitude. Two coaxial coil, same radius and equal turn also. Suppose it is n number of turns, that is identical, equal turns carrying same current in same direction. Find net field at midpoint. If this is the midpoint, then you have to find the magnetic field at this point. Okay, how you will solve? So let me solve this question. My dear student, if current flowing through this coil is in this direction, so magnetic field will be in this way. Okay, at any point, right side the conductor, that is the coil, left side the coil, the direction of magnetic field will be towards negative of x axis. So at this point we have to find the magnetic field. So we'll write the magnetic field. Suppose this is the coil 1 and this is the coil 2. Here the magnetic field due to 1, it is B1, this direction, and due to this one also the same direction because the current is same, so B2. Here all the specifications are same, even the distance are same, so the B1 and B2 will have the same magnitude. So the B net we can write, it is twice B. All right, yes, now twice B. We are having conductor now with the value of x. How much it is? It is r. Here the value of x will be r, and r, it is r itself. Now we know the formula for n turns. What is that? So we know the formula. It is B equals to mu naught NIA divided by 2 pi r square plus x square. So here the r square plus r square we can write 3 by 2. Okay, and the direction we are getting for both the coil, it is in minus I direction. Now it is mu naught Ni by this one. So let we solve. 2 will be cancelled out. Mu naught Nia divided by, it is a 2r square, and 3 by 2, that is the 2 root 2, and r square and 3 by 2, so it will be r q minus I cap, and this is your answer. You can write. Okay, pi is we left, pi is left, pi is also there. So mu naught n I a 2 pi root 2 rq. Okay, you can simplify this one also. This a is nothing but the pi r square, and you will find this pi and r square gone. So mu naught n I divided by 2 root 2r. Okay, this will be also the answer. Okay, my dear student, now let we discuss few more question. These are very important in our board examination. Okay, but before that I'll give you a homework. Let me grab this one. So here the homework. Kindly get your homework. Try to understand. This is one coil, and this is another coil, but of different radius. Through this coil the current is, suppose I1, loop L1, loop L2. This is the two coaxial coil. Okay, in this coil current is 1 ampere. Alright, in this coil the current is 1 ampere, and suppose its radius R1 is 3 centimeter, its radius R2 is 4 centimeter. Alright, I'm writing also, and I'm speaking 4 centimeter as it is placed. Okay, what should be the magnitude and direction of current in this coil? You have to find. If here the current is I2, I'm not giving the magnitude and direction, will be what will be the magnitude and direction in of current in L2, so that B at O, this is O, will be 0. Net magnetic field will be 0. This point O is 4 centimeter from a smaller one and 3 centimeter from bigger one. Okay, this is 3 centimeter, 3 centimeter, and this is 4 centimeter. You have to find for what value of I and direction thus net magnetic field due to this both the coil at O will be 0. Okay, you have to solve by yourself. Even I'm not going to give you the answer. Okay, you will solve by yourself and then you will tell me the answer. Now, as we have studied the dipole moment, my dear student, we will study one more topic. It is dipole moment of revolving electron. That is very important. So kindly give the heading dipole moment of revolving electron around the nucleus in an atom. Okay, you have to find. Let us consider an atom with nucleus Ze. Here the nucleus, nucleus is plus Ze. This is the charge of nucleus. Okay, my dear student, let me draw here plus Ze. This is the nucleus, and this is the size of atom in which electron is moving. In 3 marks actually this derivation used to ask in board examination. Suppose the radius is r and an electron is revolving around this nucleus. Suppose this is the electron and this is revolving with the constant speed v. Alright, yes, what is this v actually? This is the constant is speed. So we'll write here the V is constant is speed. Here R is the radius, and suppose m is the mass of electron. Mass of electron. Okay, my dear student. Now we are going to find here the magnetic dipole moment. Okay, so we know that current is charge per unit time. Okay, I can be written as the Q by T, and we focus over the one complete revolution. In one complete rotation, we are going to find out the current for one rotation. All right. So we will write here this as total charge Q moved in one rotation. The total time period will be how much? It is T. Now we need to find first time period. So the time period will be written as it is the total distance travel 2 pi r divided by the speed, and it is v. So we can put this value over here, and now we will have this I as Q. Q is nothing but the charge of an electron. It is E, all right, divided by 2 pi r divided by v. So v will goes up. We can write this one. Now to find here the quantity like the magnetic dipole moment, let me multiply this by mass and radius. Mass and radius, so that the equation will not affected. Now here this pi r square will be the area. Look at here carefully. E mv will be the linear momentum divided by 2 m a. 2 m pi r square will be a. Now this can be also written as a this side, I times a is equals to E, and this rp, try to remember, you have studied in rotation r cross p, it was angular momentum. We used to represent by L divided by 2m. Okay, so thus IA will be nothing but dipole moment, E L by 2m, and this is the dipole moment of revolving electron. Now we are going to find here the two quantity. This is the dipole moment, remember, dipole moment. Now we are going to discuss here the two quantity that is mentioned in NCERT and used to ask in board examination. Okay, it is one the gyromagnetic constant, and second one is the Bohr magneton. So the gyromagnetic constant, actually gyromagnetic constant is a constant value for this electron, and it is, since this angular momentum will change, can change, so the constant you will find it is E by 2m is the constant in this equation, and mu divided by L, mu divided by this angular momentum, this is called the gyromagnetic constant, which is E by 2m. E by 2m, all the things are constant, and this is called gyromagnetic constant. All right, yes, which gives the amount of gyration of electron around the nucleus. This is called the gyromagnetic constant. Remember, since this E by m, okay, charge divided by mass, it is constant. So for electron, if you will try to calculate, you will find 8.8 times 10 to the power 10 coulomb per kg. All right, this is the gyromagnetic constant. And one more topic related to this one, it is mentioned in your NCERT, it is Bohr magneton, which is also very important. So give the heading Bohr magneton. Let me grab this one. Bohr magneton. Now, what is this Bohr magneton, my dear student? So, here we'll use the Bohr postulate. Okay, the second Bohr's postulate. What was the second Bohr postulate? Actually, we'll study it in very detail. But right now, I'm telling you directly the according to Bohr second postulate. You can write according to Bohr's second postulate, which was used by Bohr to explain his atomic model, Angular momentum is nh over 2 pi, where n is the principal quantum number, which gives the different idea of the different cell. Okay. Now, as we have written this mu as EL by 2m. Alright, EL by 2m. So put the value of L from this equation and you will find mu as E by 2m and L is NH by 2 pi. Overall you will have, this is NEH over 4 pi m. And the Bohr magneton, it is the magnetic moment itself, but magnetic moment at the innermost, for the innermost orbit, and for the innermost orbit, that is n equals to 1, for the innermost orbit, this mu will be the minimum, that is the magnetic dipole will be minimum, and this will be considered as the Bohr magneton. Okay, so the magnetic dipole moment for the innermost orbit is considered the Bohr magneton. If you will try to find out the equation, since you can see this is nothing but the mu minimum, you will find it is EH over 4 pi m. After calculation, you will get mu minimum, that is the Bohr magneton, as it is 9.27 times 10 to the power minus 24, alright, ampere meter square. And this is the Bohr magneton, my dear students. Okay, so my dear students, this is all about the today's lecture. In next lecture we will start with the magnetic force. Okay, we will start with the magnetic force. Thank you, students.